So, we are in the process of deriving the linear momentum balance. We have derived that in the last lecture, but then we found that the components of the viscous stress tensor are unknowns. Why are they unknowns? We are proceeding towards getting equation which is in terms of velocities. We want to get the velocity profile. So, they are unknowns, and we need to express that in terms of the viscous stress tensor components in terms of velocity gradients to be precise. And then to understand velocity gradients, we need to understand displacement gradients in solid mechanics. So, now we are taking a diversion to solid mechanics. So, in terms of this course overview, we are traversing in this arrow in this direction, meaning taking a diversion from fluid mechanics to solid mechanics, and the topic of discussion is termed as strain. What this means we will understand as we go along. Okay. In terms of our the journey to the Navier-Stokes, we started with the Newton's law, obtained the integral form of linear momentum balance, then obtained the differential form of linear momentum balance, the left hand side, and the gravity on the right hand side. To understand the surface forces on the right hand side, we took a diversion to solid mechanics, understood stress, came to fluids, understood total stress in terms of pressure and viscous stress, incorporated that on the right hand side, and derived the differential form of linear momentum balance, the complete form. We had gravity, pressure, viscous stress on the right hand side, but we are going to use this differential form of linear momentum balance to get velocity profiles. So, our unknowns in the equation, the variables in the equation should be of course density, pressure, velocity. We cannot have other unknowns. So, the viscous stress tensor components are unknown. Now, we need to express this viscous stress tensor, the components of that in terms of velocity, really in terms of velocity gradients. Understand this velocity gradients, to have a better understanding we will understand first displacement gradient. So, we take a diversion to solid mechanics, and this number 2 indicates that it is our second visit to solid mechanics, and then these two orange blocks are solid mechanics. After discussing that, we will discuss analogously these two blocks in blue for fluid mechanics. In that, first we are discussing this block on solid mechanics. You look at terms like normal strain, shear strain, displacement gradient, and this is what we are going to discuss in this lecture and next lecture as well. So, let us get started. Of course, after we finish we will understand these terms very clearly. Okay. So, just like we had outlined earlier, for solid mechanics, the three titles shown here are the titles for the first, second and third visit. We have discussed internal forces and stress. Now, so second visit, the title says deformation and strain, and of course, third title says Hooke's law. We are going to discuss about this second title, which is deformation and strain. Now, what is the outline for deformation and strain? Okay. We are in second diversion to solid mechanics. In that, this outline for the second visit, we will discuss slowly as we go along, each bullet by bullet. Okay. So, what are the points or concepts we are going to discuss? We are going to start with types of deformation and definition of strains. There are a lot of terminologies here. I am not going to explain them right now, we will understand as we go along. So, let us just read them. Second concept is on displacement field and displacement gradient. Then we relate strains and displacement field. We define strain here, we discuss displacement field and displacement gradient. So, we relate both of them, and that is what we do here. And then we look at components of displacement, and then finally we split the displacement gradient tensor as sum of strain tensor and rotation tensor. Okay. A lot of terminologies we will understand very clearly as we go along. Okay, let us start with types of deformation. How do you understand this, visualize this? We take a plate and then let us say this subject to some force, and because of the action of the force there is change in the dimension along x direction, change in the dimension along y direction. And so, the first type of deformation which can happen is change in length, change in length. So, for example, let us say about 3 centimeters becomes let us say 3.5 centimeter, let us say it is 5 centimeter becomes 5.5 centimeter. So, there is increase in length, that can be decrease in length as well, but the first type of deformation is change in length. Okay. Now, that is what is shown here. We have a plate of delta x and delta y length and width, and that becomes delta x star and delta y star. Okay. Most of the times in terms of our figure, the continuous line represents the dimension of the solid before you apply the force, and the dotted line or the dashed line represents after you apply the force. Okay. I think remember we discussed when we discussed about difference between solid and fluid mechanics. The case of solid, it goes from one equilibrium state to another equilibrium state. I have a solid and different names are given for the solid or state before applying the force. We can call it as initial state or undeformed configuration. Okay. And you apply a force, it undergoes deformation. Okay. What does the deformation mean? For example, right now change in length. So, this is this continuous line that represents the plate in the initial state or in the undeformed state. Okay. And this dashed line represents the same plate after you apply the force, it has undergone some deformation, in this case change in length, and then it has come to another equilibrium state. Remember, for solid mechanics we said solids go from one equilibrium state to another equilibrium state. You continue to apply the force and it changes from this length to this length. In terms of area, of course, there is change as well. So, and this dotted line represents the deformed configuration. Now, instead of change in length, there could be change in angle as well, change in angle as well. What happens? You take the plate and let us say you apply a shearing stress, shearing force like this. So, what happens? In this particular case, this length almost remains same, the length of PA and PA star are almost same. Similarly, PB and PB star are almost same. So, there is no change in length, but if you look at the angle between PA and PB was 90 degrees. Now, that angle has reduced and it has become an acute angle. So, this also called as a deformation, the second type of deformation, namely change in angle. So, whenever we discuss deformation, whenever we say deformation, deformation is a very well known word used even in daily day-to-day activities, but now we have to attach a very specific meaning when we discuss solid and fluid mechanics. So, when we say deformation, we say it means that change in length and or change in angle, both can happen. That is what is shown in the figure at the bottom, where you have change in length and change in angle. This rectangle represents the state before applying the force, initial state or undeformed configuration. Now, this has become almost a kind of parallelogram. Now, if you see, the length AP has increased to PA star A star, similarly length PB has increased to P star B star. So, there is increase in length, and then look at the angle, there is a change in angle as well. This 90 degrees has now reduced. So, this example where you have both change in length and change in angle. So, in general you will have both change in angle and change in length as well. There is one more thing shown here, the plate has moved. If you see here, the original plate is here, it has moved here, and we will discuss about that later. Right now we just focus on change in length, change in angle, and both can happen together, and this is called, we call as deformation. Okay. Now, we have described this in words. Now, we will have to quantify it, and that is what we are going to do now. How do you quantify change in length, change in angle? Okay. Now, it says two measures of deformation, one for change in length, one for change in angle. Change in length of a line element is quantified in terms of normal strain. Okay. Change in angle, moment is a angle, you need two line elements, we quantify in terms of shear strain. Okay. So, let us see how do we do that. What is shown here is a solid object, okay, and that you mark 2 points P and Q, you mark 2 points P and Q, either you call them as points, later on I will call them as particles or solid particles, so that you can easily extend to fluid. Remember, you always have to take this to fluids, so we can easily say fluid particles or solid particles. So, we identify 2 points, something like this, you take a plate, then mark some 2 points here, and what is PQ? PQ is a line joining the 2 points PQ or the 2 particles PQ, and delta S is the length of the line joining P and Q. Now, I have shown one vector n, n represents the direction of the line PQ. Okay. So, what is that we have done? Taken a plate, it is in the initial state, look at the terminology, it looks like same as thermodynamics, we say no, a gas goes from initial state to final state. Similarly, for solid also we said it goes from one equilibrium state another equilibrium state, that is why our terminology is also initial state or undeformed configuration, which means no force is applied. So, you mark 2 points P and Q along a direction n, the length of that line is delta S. Now, what do? You apply a force on this. Now, the points you mark or particles you identify, they get displaced, that is what is shown here. Initially P was here, P has moved here to P star, okay. Q was here and Q has moved to Q star here. Now, and this U B represents displacement of point P, U Q represents displacement of Q, we will discuss this later. Now, focus on the line P Q has become the line P star Q star, and the length has become from delta S become delta S star. Okay. Now, strain, the word strain is not new to you. You would have usually discussed strain for something like a rod like this, and you would have defined strain as change in length by original length. Okay. Same meaning here as well, but with a small difference, that is what we are going to discuss. Okay. So, or you would have discussed a thread and then change in length by original length. Okay. Let us do that now. Let us define normal strain in this way. I will explain what is the definition of the, what is the meaning of the definition. This definition of the shear strain, we will come to that shortly. Now, these are the conditions, we will discuss that as well. Okay. Okay. Now, what is that we have defined? What is left hand side? The normal strain is represented by epsilon, and then we have a subscript n. Why subscript n? We have taken a, okay, this line element means that the line joining the points PQ. Okay. Now, we said the line PQ is along direction n, that is why we have used subscript n here. I will come to the P within bracket shortly. Now, we defined normal strain as change in length by original length, same definition. So, delta S star is the, let us say the final length, delta S is the initial length divided by initial length. Now, what is the difference between what you already know and this definition? What you have usually know, you took this original length and then the final length, took the difference divided by the original length. This gives you normal strain for average over the entire length of the rod or thread. But remember, we are going to go back to our linear momentum balance, all of them are valid at every point. So, we need a point form of strain, is it okay? What you know is the definition of average strain. If there is variation of strain along the length of the rod, then we need a definition of normal strain which is valid at every point. What do we do? Here we took P and Q slightly separated, make Q tending to P and that is what this means. Limit of q tending to p, what will happen? Delta s will tend to 0. Same definition in the limit of, what does it mean? You have just p here, q here very near to each other, then this becomes the definition of normal strain, and that is why here within bracket I have written at p. So, what does this definition tell you? Normal strain at p, and of course, you require a little more imagination. You should imagine at a point, but a small line along n. It is not one point, then you cannot, it is at a point, but still you should imagine a. So, you are at a point and imagine a, you are at a point, okay, you are at a point and imagine a small line, very small line along direction n, and what is the change in length for that line? Of course, divide by the original length gives you the definition of local normal strain. Significance is known to you, change in length by original length, only difference, or of course, that is required for this our scope of this course is that we have defined normal strain locally. We will see an example. In fact, using this we can find the normal strain at every point along the rod or along the length of the thread. Okay. And that is why we have taken q tends to p and delta s tends to 0. Now, if there is increase in length, of course, epsilon n is greater than 0, and if it is decrease in length, epsilon n is less than 0. So, several aspects to be looked to be focused on in this definition. First is epsilon, normal epsilon subscript n, normal strain. N does not represent normal, okay, normal strain. N does not represent normal strain, n is used to represent the direction of the element for which you are defining the normal strain. Okay. Please keep that in mind. And on the right hand side, change in length by original length in the limit of q tending to p, delta s tending to 0. Now, let us move on to shear strain. Shear strain we said is used to quantify change in angle. Moment I say change in angle, I need 2 line segments, which means I need 3 points. That is what is shown here. In the undeformed configuration, initial state I have points P, R and then Q. So, I take a plate and then mark points P, R, Q, and then I mark such that the angle between them is 90 degrees. Now, P, R can have one direction, P, Q can have one direction. That is why we have 2 directions n and t. For the case of normal strain, there is only one line element. So, only one direction is enough, that is why we denote it by epsilon n. But when you come to shear strain, you are talking about angle between 2 line elements, which means that 2 directions are required. That is why you have 2 directions n and t. So, what is that we have done? We have taken line elements P r and then P q, they are along directions n and t, and the angle between them is 90 degrees. Now, we apply a force, the body gets deformed, goes to another equilibrium state and then stops deformation. In the deformed state, in the final state, r has got displaced to r star. I start using slowly more formal words as moved to, instead of saying moved to I am using the word displaced to, okay. And then P has got displaced to P star, Q has got displaced to Q star. Now, what happens to the angle? There is a change in the angle between the 2 line elements. The angle between R, P and Q is 90 degrees. The angle between R star, P star, Q star is in this case lower than 90 degrees. Of course, can be more than that. This difference, change in angle, is quantified as shear strain. Now, let us look at the definition. The shear strain is represented by the letter gamma. Subscript, 2 subscripts are required. Subscripts are n and t, and I will come to that point P as we have discussed earlier. It tells about change in angle. The initial angle is pi by 2, the final angle is r star, P star, Q star. As we have discussed for the case of normal strain, I need definition of shear strain at a point. So, what should happen? This Q should become as close as possible to P, R should become as close as possible to P, and this change in limit of Q tending to P, R tending to P is your definition. Of course, pi by 2 is just a constant, is your definition of shear strain. Okay. Now, how do you imagine? Once again, you imagine at a point a small line segment, another small line segment, okay, and those which are at 90 degrees to each other. Why small? We are saying q tending to p, r tending to p, but still at a point you are imagining two small line segments perpendicular to each other. Of course, a little difficult to imagine, we are saying point, but telling two lines etc. As you go along, you will get practice to that. The case of normal strain, at a point imagine a small line. Case of shear strain, at a point imagine two small line segments perpendicular to each other, and what happens to their angle. Why this small point? Because we need definition of local normal strain, definition of local shear strain. We want to describe what happens to the length, change in length, change in angle at every point in the body. That need not be same. In the case of a simple rod, it may be same throughout the rod or throughout the thread, but in a general body, when you subject it to force, this normal and shear strain can vary or will vary most of the time along the throughout the body, and that is it. That is why we want a definition of local normal strain and shear strain. Of course, in terms of magnitude, if this angle reduces, this angle becomes acute, then the shear strain is positive. If it is increases, becomes obtuse, then the shear strain is negative. If it increases, it becomes obtuse, then the shear strain is negative. Okay. So this tells you decrease in angle, this tells you increase in angle. Coming back to this point P, why do we say as point P? I said imagine a point, at that point we have two line segments. So this finally it is shear strain at point P only, though we have P, Q, R etc. Finally the definition is for shear strain at point P only. Okay. Now we have defined this normal strain along line element which is along n, and shear strain for two line elements along n and t. But what we are going to use in our discussion is only line elements along our coordinate axis, okay, and that is what we are going to see now. What is the analogy in terms of stress discussion? Remember, we said any plane, and then we had a stress vector resolved along the particular axis. Then we said we are going to resolve along x y z axis, then we took planes which are parallel to our coordinate planes. Similarly, here we have a very general definition, so we took n, nt etc. But now what is that we are going to use subsequently are line elements which are along x axis, along y axis. So just let us write down the normal strain for line segment along x axis. Let us write down the definition of normal strain for line segment along x axis. This is for line segment along any direction n. Our line segment now is along x axis. So replace n with x. So epsilon x represents normal strain for line segment along x axis. What do you mean by that? Take a line segment in an object, you mark 2 points along x axis p, q. Earlier it was any direction n, now you will be marking along x axis only, and then you will be finding out what is the changing length by original length. Okay. Similarly along y axis, and then similarly along z axis. Okay. These are specific forms of the earlier expression, and we will be using only these normal strains, okay, for line segments along x axis. And for the case of y axis, you will take a line element p q like this. Okay. Okay, now for the case of shear strain, we had two subscripts, okay, but for the case of normal strain we have only one subscript. One subscript is sufficient, but to be uniform we will represent normal strain using two subscripts, namely epsilon xx, epsilon yy, epsilon zz, okay, because there is only one direction here, but to have uniformity we will use two subscripts as epsilon xx, epsilon yy, epsilon zz. Okay. So our nomenclature for normal strain along x axis will be, for line segment along x axis will be epsilon xx, accordingly other directions. Now we have looked at the definition for shear strain for two line elements along n and t direction. Instead of that, we will take two line elements along x axis and y axis. So our nomenclature becomes gamma xy, gamma xy. Okay. Gamma xy represents shear strain between two line segments along x and y axis. Similarly, gamma yz, we take two line elements along y and z axis, of course in the case of 3 dimensional case, and then gamma zx, shear strain between two line segments along z and x axis. Okay. And by definition, how do we define shear strain? Shear strain represents the difference in angle between initial state and final state. So, does not matter whether it is gamma nt or gamma tn, it is same. So, our gamma xy will be equal to gamma yx, just angle. We are, remember, we are not considering any direction here, that will come to the later, but right now just difference in angle. So, difference in angle is, does not matter gamma xy or gamma yx. Similarly, gamma yz equal to gamma zy, gamma zx equal to gamma xz. Okay. So, we have defined normal strain, shear strain locally, that is important, for elements along any direction n and two elements along n and t. We have adapted that or applied that for line elements along x, y, z axis for normal strain, adapted that for line segments, two line segments along x and y axis, y and z axis, z and x axis. Okay.